All right, friends, welcome back. Hope you had a good weekend. We're going to dive right into chapter 18 today. And this is one of the more difficult chapters that you'll face in this class. There's just sort of a lot going on. And so we'll take it step by step, and it will be useful if you can connect what we're doing today with things that you've seen before. In chapter 18, the theme is what's called carbonyl condensation reactions. That means a reaction where two different carbonyl compounds are coming together to form one molecule. But it will be helpful if you can see this as an extension of what you've learned in previous chapters. For example, in chapter 18, the nucleophiles are still going to be enolates. So it's going to be similar to what we did in chapter 17. The difference is, in chapter 17, the electrophiles were mostly alkyl halides, or at the very end, a halogen like bromine. In chapter 18, the electrophiles are going to be other carbonyl compounds. And of course, if those carbonyl compounds have no good leaving groups on the carbonyl carbon, you expect to see a nucleophilic addition product. And if there is a decent leaving group on the carbonyl carbon, you expect to see nucleophilic acyl substitution. And for the most part, that's going to be our theme with a little bit of variation, but in general, that'll be our theme. Today, we're going to be dealing with the nucleophiles as enolates, and we'll be dealing with addition products. That is, the electrophiles aren't going to have any good leaving groups on the carbonyl carbon. But I encourage you, as we deal with each new reaction, not to see it as a separate thing to memorize unconnected from everything else, but to just see it as examples of principles that you've already learned. So let's start in with an example of an enolate reacting with a carbonyl compound. And to set this up, we're going to just review briefly some things you already know. When you put a ketone like this one in the presence of a base like hydroxide, you are already used to, based on chapter 17, the idea that the enolate, the hydroxide, can remove the alpha proton to a very small extent to give you this enolate. And the reason you know that that proton removal happens only to a very small extent is that you know the pKa of this alpha proton is around 20, whereas the pKa of water is around 16. So, for the most part, most of our starting material most of our ketone is present and doesn't exist as the enolate. In fact, we've even said it's probably less than 0.1% of the enolate present, right? And we've drawn the resonance structure of the enolate in which the negative charge is on the alpha carbon and the other one in which the negative charge is on the carbonyl oxygen. We've said for the most part when enolates react as nucleophiles that in general they are more nucleophilic at the alpha carbon. And in some ways that's a little bit counter to your intuition, because you are used to thinking about this as being a better resonance structure because the negative charge is on the electronegative oxygen. And that's true, that is a major contributor. But if you actually do the math of MO theory, there's more HOMO on the alpha carbon. So the molecule is more reactive as a nucleophile on the alpha carbon. Of course, you've seen enolates get protonated before on the oxygen to give you an enol tautomer, but we've said in general that enol tautomer is less stable than the ketone, and so we don't form very much of the enol. The other thing we've learned to worry about for carbonyl compounds is what if this oxygen, what if the OH minus nucleophile attacked the carbonyl carbon of the ketone rather than remove the alpha proton? If we did that, we would simply get, and I'm skipping a mechanistic step, but we would get what we learned in chapter 14 was the ketone hydrate, which again is present in water, but doesn't really lead anywhere. So these are several things that we have in our minds all going on when we have a ketone and it's in slightly basic solution. Okay? Today we're going to focus on the fact that the enolate is a nucleophile and the ketone is an electrophile. And we're going to worry about something that we probably should have worried about before, which is, I guess I meant this, greater than 99% present as the ketone. If you've got the nucleophile in solution present with the electrophile, they can start to react with each other. So let's show how that would happen. Let's have the ketone nucleophile attack the carbonyl carbon of the enolate nucleophile, rather, attack the carbonyl carbon of the ketone electrophile. So to show that, I'm going to draw the enolate nucleophile here. We'll draw the carbonyl carbon of the ketone here. We'll point out that that ketone doesn't really have any good leaving groups on it, so that when the alpha carbon of the enolate attacks the carbonyl carbon of the ketone, we're going to get a new sigma bond, and we'll break the pi bond, and that's going to get us to this intermediate, and I will draw the new bond that we formed in red. Here is the oxygen of our tetrahedral intermediate. Here are the two carbons that are attached to what used to be our carbonyl carbon. In pink is that negatively charged oxygen, and then I'm going to keep highlighting the nucleophile that was our enolate in purple. Now, whenever we have a tetrahedral intermediate, we ask the question, is there a good leaving group relative to a negatively charged oxygen? And the answer here is no, those methyl groups are not good leaving groups. I've drawn a reversible arrow here to indicate that that negatively charged oxygen could kick off the enolate as a leaving group. And that happens sometimes, but for our purposes today, we won't worry about that backward step, and instead are going to think about what can happen next. So, no other good leaving group on the carbonyl carbon. That means that we're stuck until the conjugate acid of hydroxide, the thing we used to generate the enolate in the first place, comes along and protonates that oxygen to give us this product. Again, in red is the new bond we just formed in that nucleophilic attack step. Here is the enolate nucleophile, here's the oxygen, here's the carbonyl carbon. Okay, so we've made a new carbon-carbon bond. The structural pattern in this product is useful and important to recognize. If we start counting from the carbonyl carbon of the enolate, this is the alpha carbon, and then this is the beta carbon. And our product here is a beta hydroxy carbonyl compound. And the reaction that we've just done is called the aldol reaction, and this is an aldol product. It's called the aldol reaction because you start with an aldehyde or a ketone and you make an alcohol as part of your product. That's one of the famous name reactions in organic chemistry. It has a name that we refer to all the time. You'll do this reaction if you haven't already in the 353 lab. Okay, questions about that? Yeah.
With the aldol product coming from a reaction that is not very favored at equilibrium, is it only really relevant because the non-favored reactant that the enolate is showing up and disappearing as opposed to the product?
Right, so we don't ever form very much of the enolate. but as that enolate is formed, it is consumed by attacking the starting material, and that causes more enolate to form. In general, because this is an equilibrium process, yes, the process can go forwards or backwards, and which way it goes depends on which options are more stable. And you can sometimes tweak that and change the conditions. We will see that biology actually does a retro-aldol reaction. It takes a beta hydroxycarbonyl compound and goes back to the carbonyl, what we would consider starting materials for the aldol product. So in general, yes, the reaction proceeds because as the enolate reacts with the ketone, that pulls the equilibrium forward. You can, and for our purposes in this chapter, generally we'll consider the aldol products to be more stable than the starting materials, and so you can expect the reaction to go forward. Okay, good. Others? All right, now there's one other thing that can happen at this stage one other thing that can happen to the beta hydroxycarbonyl compound, which we're calling the aldol product. One of the things that you may have noticed is that we regenerate hydroxide in this process. So the process is actually catalytic in hydroxide. You don't need a ton of hydroxide, just a little bit to make the reaction happen. The other thing you may have noticed is our product still has alpha protons. So OH minus can remove the alpha proton to create a second enolate. Here's that, what I will call the second enolate. And I'm going to continue to highlight what used to be the carbonyl carbon, the oxygen, and the carbons that were from the nucleophile. I'll keep highlighting in red the sigma bond that we already made. What will happen next is the negatively charged alpha carbon, that lone pair electrons, are actually going to act as a kicker offer to kick down and kick off OH minus as a leaving group. Now, you may be worried about that because in 351, it was sort of a major theme that OH minus is a bad leaving group. You had to do things to OH minus first to make it a good leaving group. More recently, you've seen us allow OH minus to be a good leaving group provided that the kicker offer is strong enough, right? We've done things before, for example, in where we've had a negatively charged oxygen totally fine to kick off OH minus. So our real consideration as to whether OH minus can kick off, as to whether the kicker offer can kick OH minus as a leaving group is the thing that leaves more or less stable than the thing that did the kick offing. Sorry, that's not good English, but I think it's fine for today. So I'm going to draw the product that comes from this reaction where OH gets kicked off. Here's the OH leaving group. Here's in purple the portion of the molecule that used to be our enolate. Here's what used to be the carbonyl carbon, and there's what used to be the carbonyl oxygen. Now our consideration as to whether this last step is reasonable is related to, is the thing that left, OH minus, more or less stable than the thing that did the kicking off? And to do that, we can simply think about pKa's of conjugate acids. For OH minus, it's water, pKa 16. For this enolate, the conjugate acid is just the ketone, which has a pKa of 20. So yeah, we would say that a negatively charged carbon of an enolate is a strong enough kicker offer to get rid of that oxygen. And the second product that we get, or rather what I've drawn here, is actually an example of something you've seen before. This is an alpha-beta unsaturated carbonyl compound, and it is also an aldol product. Okay, questions?
What do we call this product?
Yeah, we call it alpha-beta unsaturated because there's a pi bond between the alpha and the beta carbons relative to the carbonyl carbon. They are both aldol products. Yeah?
What traits exactly make it an aldol?
What traits make it an aldol product?
Yeah.
Okay, I guess the aldol reaction is always a reaction of an enolate with a carbonyl, and you've got two options for products. Both of them are going to have new sigma bonds between alpha and beta carbons. The structural pattern you're looking for is beta hydroxycarbonyl compound, or its dehydrated version, the one with the double bond between alpha and beta carbons. Yeah, so we want to anticipate both of them as potential products, in part because they're in equilibrium with each other, and which one forms as the major product is going to be totally context dependent. It's going to depend on the situation. It really depends on which one's more stable than the other. You're not going to know that in advance, so you need to anticipate both. In a predict products question, either of those two, either the beta hydroxy or carbonyl compound or the alpha beta unsaturated carbonyl compound are acceptable aldol products. So, for example, on my exam, you're not going to see a multiple choice question where it's like, which of these is the aldol product, and both of those are options, and you have to pick one and hope for the best. It would just be one. I would show you one of them, and you'd pick the one that is an aldol product. In a synthesis, you could use either of them. In a mechanism question, you'll know where you need to get to, because in a mechanism question, you're given starting material and product, and so you know where you need to go. Other questions? Yeah, go ahead.
Since we've regenerated the hydroxide, the OH, does that mean that we're going to take off another hydrogen on that alpha?
So it's a good question. If we regenerate hydroxide, can we remove a proton? You've noticed I haven't drawn it there, but if I move this a little bit out of the way, you can notice that alpha carbon still has one more proton. The answer is, once you make the alpha beta unsaturated carbonyl compound, that proton is no longer acidic. It's kind of hard to appreciate it unless you build a model. Remember that the one thing that made alpha protons acidic to begin with was that their conjugate bases are stabilized by resonance. Also, we talked about alpha protons being able to line up with the pi star of the carbon-oxygen antibonding orbital. This CH bond is held perpendicular to the pi star, and if you removed it, the lone pairs there would be in an sp2 orbital perpendicular to the pi system and unable to conjugate with it. So removing this alpha proton doesn't generate a resonance stabilized conjugate base, so it's not very acidic. All right, what else? One thing I forgot to say at 9 o'clock is the important point that what we've just done here to the beta hydroxycarbonyl compound is an elimination reaction. But it's an elimination reaction via a mechanism you haven't seen before. So in 351, you saw elimination reactions like this, where a base removed a proton adjacent to the leaving group. This is an E2 mechanism, and then you make the pi bond and the leaving group left. That was called E2. You also saw a mechanism in which a leaving group would leave first to give a carbocation, and then a base would remove the proton, and give you the product. And that mechanism was called E1 because the slow step just involved the starting material and not the base. This is a mechanism that is an elimination reaction, but it's distinct from those two earlier options from 351. In this mechanism, we first remove the proton, and that is fast. And then in the second step, which is slow, the electrons kick down and the leaving group leaves. This reaction mechanism is called E1CB. CB stands for conjugate base. The conjugate base is the second enolate. You make the conjugate base of the ketone first, and then the elimination reaction happens. That's an important point in the aldol reaction. I said that at 9 o'clock, and I'll have to say it again when they come back because I don't think that it may be a subtle point. In particular, it is not correct to show in the aldol mechanism removing the proton, making the pi bond, and the leaving group leaves all in the same step. Instead, you must form the enolate first, and then the elimination happens. All right. So let's work on this a little bit in a retrosynthesis sense. As I said, you need to be able to look at those two aldol products and recognize both of them as things that could have formed via the aldol reaction. So we'll go straight to the difficult stuff. Let's think about this as a product, and I will go ahead and tell you that this is an aldol product. So now you tell me, what structural pattern does that fulfill that makes it an aldol product?
There's the double bonded carbonyl
Okay.
with an attached beta carbon, which
Okay.
has a double bond.
Good. So you've noticed here's a carbonyl carbon, here's the alpha carbon, here's the beta carbon. Good. That makes it an alpha beta unsaturated, what we've called an alpha beta unsaturated carbonyl compound. Good. Which bonds? Well, I just highlighted them in red, so sorry, I shouldn't have done that. When you see the alpha beta unsaturated carbonyl compounds, the bonds in red are the ones that were made in the aldol reaction. Now you tell me which atom, I'll highlight it in blue once you tell me which atom used to be the carbonyl carbon of the electrophile. Beta, good. Where's the carbonyl oxygen? Not there anymore, it was eliminated as OH minus, right? Which atom used to be the one that did nucleophilic attack? The alpha carbon, right. This was the enolate, okay? Everything else is just spectators. So if I'm thinking backwards, and ultimately I want you to get to the point where you can think all the way backwards to what the starting material is. For our purposes here, we're going to think backwards through the mechanism. The immediate precursor to the dehydrated product is the one that looks like this. That is the second enolate, the one where the alpha carbon is negatively charged and there's an OH on the beta carbon. We'll go ahead and label things like we did in the mechanism above. Okay, does that make sense? That's one step backwards. Of course, the step immediately previous to that one was just the beta hydroxycarbonyl compound. That is another example of the aldol product. Again, here is what used to be the carbonyl carbon. Here is what used to be the carbonyl oxygen. Here's that, alpha carbon that was the nucleophile. All right, we'll label that in purple. Now, here's the, and of course the immediate precursor to that was the tetrahedral intermediate where the negative charge was on the carbonyl oxygen. Now let's think backwards through the actual sigma bond forming step of the aldol reaction. If this is indeed the bond that I made, then what should it look like immediately prior to that? What am I going to draw? Let me draw just I can draw it in exactly the same shape. Here's the carbonyl carbon, here's the alpha carbon. The ketone is still there. What should be on the alpha carbon? Should have a negative charge. That's going to be my enolate, right? What should be down here on what, used to be in what was in my product, the beta carbon? What's going to be on that one? That's my ketone electrophile. Good. And at that stage, the problem is basically done. My starting material is just the conjugate acid in which the alpha proton hasn't been removed yet. And if I wanted to redraw this in a way that concealed the fact that we were going to make a 6-membered ring in this aldol reaction, I would see that it's a 7-carbon chain with ketones on either side. 1, 2, 3, 4, 5, 6, 7. Okay? So that's thinking backwards from an aldol product to starting material. Yeah?
So how would you convert that from having the two ketones to just one of them becoming?
So yeah, the question is, how do I start with something that has 2 carbonyls in it and just expect to form one enolate? The answer is carbons 1 and 7 are identical by symmetry. So it actually doesn't matter which one I remove. I can only make no matter which one I remove, I get the same enolate. Yeah?
Do we have anything apart from the alpha carbon?
Here? No, because I was showing you the starting material. This is the enolate where we already have a negative charge on the alpha carbon, and this is the starting material. So that alpha proton has to be removed first before you get to the enolate. All right, others? Yeah?
For a base for the starting materials, would we have to use LDA versus hydroxide due to reduced selectivity?
So that's a great question, and that leads us into what I want to talk about next. You've noticed there's, I'm going to erase the orange alpha proton on 7 because you guys have accepted those are the same kind of proton. But there are 2 different kinds of alpha protons. You've got orange alpha carbon and you've got purple alpha carbon. And you're worried about enolate regioselectivity for good reason, because in chapter 17, which enolate we formed determined which alkylated product we should get, right? If you formed the enolate under reversible conditions, you would expect to form the more substituted enolate because it's more stable. If you form the enolate under irreversible conditions, you could expect, with LDA, you could expect to form the less substituted enolate. You're going to see in just a second that the reason that mattered in chapter 17 is because the step after forming the enolate, the alkylation step, was totally irreversible. So we did reversible enolate formation, but once we did the SN2 reaction, we never went back to the enolate. You're going to see in contrast that the aldol reaction is reversible from start to finish. So while enolate stability matters, it's not the only thing. But let's actually walk through that just a little bit more slowly. We're going to take this starting material, and you've already seen what happens when this starting material makes the less substituted enolate. I'll just draw that less substituted enolate here, and we're going to point out that it is less stable. And then you've seen the product that we get from that. I'm skipping ahead a ton of steps. Hopefully this is okay. We've already thought backwards through that product. So this is the product that we get, the alpha beta unsaturated carbonyl compound, the aldol product that we get from that enolate. Okay? Now let's imagine that we form the other enolate, which I'm going to draw in purple, in which we put the negative charge on the more substituted purple alpha carbon. I'm going to keep numbering the atoms here to help you predict a little bit better what you anticipate the product to be. And we won't jump straight ahead to the final product. We'll do this stepwise. What do you think happens when the purple alpha carbon, the negative charge on the purple alpha carbon, attacks the blue carbon 6, the carbonyl carbon? What size ring should that make? 4, right? 1, 2, 3, 4 atoms. So let's just draw a 4-membered ring. Let's let this one be 3, 4, 5, and 6. Carbon 6 should have, let's see, a negatively charged oxygen on it. And it should also have the methyl group carbon 7. Carbon 3 should still be bonded to carbon 2, which is the carbonyl. Carbons 1 and 2 there. All right. And then, of course, we could think onwards to protonating the OH group, the oxygen to get to the beta hydroxycarbonyl compound. And we could also think forwards to the dehydrated product that would look like this. Okay? So I've skipped ahead, and if you need to go back through and do that stepwise, that's fine. This is the purple aldol product. Notice that I've used deliberately arrows that are reversible here to indicate that the aldol products, orange and purple, are in equilibrium with their respective enolates. And we're not doing this today, but another time we will actually go through an example of a retro-aldol reaction where we start with the alpha-beta unsaturated carbonyl compound and we go all the way to the ketone and enolate starting materials. Unlike enolate alkylation, where the last step, the alkylation step, the SN2 reaction was reversible, for the aldol, it was irreversible. Unlike enolate alkylation, where the last step, the SN2 reaction, was irreversible. In the aldol reaction, the last step is fully reversible. And what that means is that the stability of the products matters too. We've already pointed out that the orange enolate is less stable and the purple enolate is more stable. But now I want you to look at those two products and tell me whether you expect one to be more stable than the other. What do you think? What's the major issue there? What might be more stable? Go ahead.
Lack of resonance.
Okay, lack of resonance in what way?
So for the more stable enolate, the hydrogen the oxygen will break down, and it'll create a more substituted product.
Okay.
This is the less stable enolate. It'll create a less substituted product.
Ah, I see. So you're thinking about alkene substitution. You are right that this product has a more substituted alkene than that one. That's absolutely true. What other factors do you see? Go ahead. Ring strain? Is that what others are going to say? Yeah, so in the 6-membered ring, the sp2 carbons are supposed to have bond angles of 120 degrees, and that's actually the ideal internal angle for a 6-membered ring, or rather for that at least a hexagon. So 120 degree bond angles are totally fine in a 6-membered ring, not so much in a 4-membered ring, where an sp2 carbon needs to be 120 degrees, but in a 4-membered ring it's constrained to be 90. So yes, ring strain makes the purple aldol product much less stable, whereas the orange aldol product is more stable. As a result, it does not matter that the more stable product comes through the less stable enolate. The more stable product is still the major product. Okay? When products are in equilibrium with starting materials, the only thing that matters is not the stability of the intermediates, but the stability of the products relative to each other. Yeah?
In the purple starting material, what keeps the pi bond from going to the 2,3 carbon and then the negative charge going to the oxygen?
Right, so you're thinking about what would happen if I drew a resonance structure like this. And could you expect this oxygen to attack that carbonyl? Because you're noticing that would be a 1, 2, 3, 4, 5, 6-membered ring. You wouldn't be surprised to see that kind of thing happen. And if you did, we would call that an O-alkylated product, an oxygen that had been modified on the carbonyl, on oxygen that had done the attacking rather than the alpha carbon. I told you in general enolates are more reactive on the alpha carbon, and that has to do with some MO theory considerations that put more of the HOMO on the alpha carbon than on the oxygen. And the other thing is, if you attack from the alpha carbon, you get to keep the carbon-oxygen pi bond. If you attack from the oxygen, you lose the carbon-oxygen pi bond and you get a carbon-carbon pi bond. It turns out carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds, so that's one reason not to expect this to happen. Yeah, if it happened, you wouldn't be surprised to see it, but for the aldol reaction, we won't predict that in general. Okay, what else? So I just want to make this point about relative stability with sort of an energy diagram. So I'm going to copy some intermediates here. We're going to put some of the starting materials and stuff here. We're going to put our ketone and OH minus here in the middle. We're going to put the enolates higher in energy than the starting material, though we're going to put the more stable enolate lower in energy than the less stable enolate. So we'll put that a little bit up higher. And then we'll put the products here, but on either side, but we're going to put the aldol product that's purple a little bit higher up in energy than we'll put the aldol product that is orange, because we've said because of ring strain, the orange aldol product is indeed more stable. So our energy diagram is going to look something like this. We'd go uphill to the more stable enolate and then downhill to the aldol product. We got to go even more uphill to the less stable enolate, but we get to go more downhill to the more stable product. And ultimately, product ratios are determined if the products are indeed in equilibrium with the starting material, which I've said they are. Product ratios are determined by the relative stability of the products. Okay? Yeah.
So main takeaway is it's okay to use hydroxide in this situation to get the more stable product.
Yep, it's okay to use hydroxide. It gives you the more stable product. In fact, you want to use hydroxide because it's cheap and the reaction's catalytic. At the end of the day, we regenerate hydroxide. So it wouldn't make sense to use expensive LDA when you don't need to. Yes?
So this example is obviously with a molecule that only has 7 carbons. If there were more, would you get a more even split? Because if you have like if you're choosing between like a 9-membered ring and a 7-membered ring.
Sure, yeah. You could imagine a case where it would not be so clear cut, where you might have a 9 and a 7 like that. And in that case, you would expect to see both. Okay. Well, let's now show you, in both of these reactions that we've done, a molecule is either reacting with another copy of itself or the molecule is reacting with itself. What we've shown you here is an example of what's called an intramolecular aldol reaction. What we want to do now is see whether we can do reactions with an enolate that's derived from a different molecule than the electrophile is. We call this the cross-aldol reaction, and the question we want to ask is, can we control who is the nucleophile enolate versus who is the electrophile? So to illustrate this point, let's imagine having two different carbonyl molecules in the same solution with OH minus. And you've got this aldehyde and you've got the ketone. Now, for the purposes of this discussion, we're going to color the ketone purple and the aldehyde orange. And we'll also draw the enolates that form in a small amount from the aldehyde and the ketone. We have the aldehyde enolate and the ketone enolate. And the issue here is that the ketone enolate can react with the ketone to give me what I will call a self-aldol product. But the ketone enolate could also react with the aldehyde electrophile to give me a cross-aldol product. In what we're doing, the things on the bottom are nucleophiles, and the things on the top are electrophiles. And of course, I'm also worried about the aldehyde enolate attacking the ketone electrophile. And the aldehyde enolate could also attack the aldehyde electrophile to give me a self-aldol product. In other words, I'm expecting to get two self-aldol products and two crossed aldol products. Here's the self-aldol product from the ketone. I'm just going to draw the beta-hydroxycarbonyl compound rather than attempt to draw that and the dehydrated product. In red is the bond that we made. Here is the cross-aldol product from using the ketone as an enolate and then reacting with the aldehyde. We'll label those in the aldehyde and ketone portions in orange and purple respectively. So this is the self-aldol product. This is the crossed aldol product. Then here we'll show the aldehyde enolate having reacted with the ketone as an electrophile. This is the crossed aldol product from that reaction. And then over here we'll show the aldehyde having reacted with, the aldehyde enolate having reacted with a copy of the aldehyde to give me the self-aldehyde aldol product. I'm tired of drawing all of that. Are you tired of drawing all of that? Yeah. In other words, it's a mess. And I haven't even added the 4 other dehydration products, the alpha-beta unsaturated carbonyl compounds, which I would expect you to be able to draw, but we're not doing that at this point. We're not going to do that right here just to save space. So, is there a better way? Is there a way for me to control which of the starting materials is going to be the carbonyl, going to be the enolate, and which is going to be the electrophile? So we'll talk about some workarounds for this problem. The first is to use as an electrophile a carbonyl compound that lacks alpha protons so that it can't be the enolate. An example of that would be, say, keep our same ketone to make an enolate, but the electrophile portion we'll use is this one, in which the alpha carbon has no protons. So the aldehyde here has to be the electrophile. It cannot form the enolate. So I could remove the proton from the starting ketone to get me the ketone enolate. And then I could hope that that enolate would attack the orange carbonyl carbon to give me the crossed aldol product, which would look like this, and I'm just going to abbreviate the benzene ring with pH. And that would give me the cross aldol product, and I don't have to worry about the potential 2 other aldol products where this would act as a nucleophile. Now, there's one thing I'm missing. Is there something that's going to go perfectly, or is there something else that could go on here? What's the thing I'm missing? Self-ketone aldol, right? Yeah, I still expect to see the purple one attack, making up chemistry at this point, purple one attacking itself. So you would still see some of the self-aldol reaction. So that potential solution is decent, but it's not perfect. You can use it in a synthesis if you've got no other choices, but there are some other things that you can do. A second strategy is to use as a nucleophile a carbonyl compound with what I will call crazy acidic alpha protons. That is, you want to make the alpha protons of the one you want to use as a nucleophile so acidic that there's no contest. So here is, we'll use this aldehyde as our target electrophile. We'll use this beta dicarbonyl compound as our target nucleophile. The point is the pKa of this proton is 9, whereas the pKa of that proton is 17. So by a factor of 100 million, this proton is more acidic. If I add OH minus, I'm going to make, because OH is a really strong base relative to that very acidic proton, I'm going to make 100% of this enolate. That enolate is never ever going to see its corresponding conjugate acid and won't ever be able to attack its conjugate acid because there's none left by the time the enolate forms. Instead, the only thing that can happen is that that enolate attacks that carbonyl carbon. We'll skip ahead straight to the aldol product rather than draw the mechanism. Here's the new bond that you make, and here's the OH group from the aldehyde. I'm highlighting the enolate portions in purple and the aldehyde portions in the aldehyde electrophile portion in orange. So that'll work, though you're somewhat limited because you got to choose an enolate that has, where your starting material is a beta dicarbonyl compound. The last and perhaps most versatile approach is called the directed aldol. And in this, your strategy is to use LDA to make an enolate in 100% yield first. And you do that before you even put the molecule that you want to be the electrophile in. And then, and only then, in a second step, you introduce the carbonyl electrophile. You've got to be really careful, and you've got to keep the reaction cold, and you probably got to add the electrophile slowly. You don't want the enolate that you make in the first step to be able to deprotonate the alpha carbon of your second carbonyl compound. As soon as you get a second enolate, you're going to get a mess. But this directed aldol works pretty well. Let's see, we got like 15 seconds left, so I'm happy to leave today's class on a cliffhanger. And we will come back next time and finish it. All right, see you Wednesday. You bet.
First strategy, can you use a protection group on the ketones to force 100% across?
If it's a nice idea if you made it, anything you could do to the ketone to do that would make it not reactive as an electrophile though. Like you could think, oh, let me make an acetal. That's great, but then the pi star is gone, so it's not an electrophile. Yep.
Perfect.
Yep. Hey.
I was just wondering, so I have a meeting soon, but I was wondering, are you still going to be going over like the test and like questions?
Sure, I'm happy to talk about specific items on the test. Have you got access to the review video? So there's something specific you want to ask about?
Okay, not at the moment, but
Okay.
if I have any questions.
Yeah.
On Wednesday.
Yep,
Okay.
that's fine. Yep, you bet.
You have the test back?
I do.
Perfect. Do you mind if I go up with you?
Yep,
to
you
the
can
office?
head up right now.
Okay.